Hello, I'm Dr. Lawrence W. Moore, and welcome to this edition of Sunday Night Synthesis. This week, many of you have seen that I put out the new, sleeker version of LWMRAC with its basic modules, and little by little, I'm going to be adding more modules. And if you follow the Learning Synthesis with Pure Data series, you'll see, beginning in Series 2, Episode 5, how these modules are put together. So if you want to do some development on it, or if you want to apply some of these concepts to your own work, you'll be able to see how things were made. But tonight's episode is going to be about granular synthesis, because I had a viewer request about this topic, and I aim to please. Right, Crafty? Oh yeah, we do aim to please. Crafty, man, you're kind of hiding back there. Let's get you in the picture better. There we go. Oh. I shouldn't be doing this focusing stuff like live on camera, but you know, we're just a cottage industry here. So anyway, me and my Minecraft pig are going to be showing you how to do granular synthesis, which means this stuff over here in Pure Data is going to make sense to you by the end of this episode. Alright, so let's do it. Okay folks, I'm just starting at my website to point out LWMRAC. What we're building tonight, or what I've already built and going to be guiding you through, is some examples of granular synthesis that I made based on a source that I'll show you in a minute. And I'm going to eventually be adding a granular module to LWMRAC. Now this just came out, this version of the new sleeker redesign version of the basic modules, but I'm going to be adding plenty of other standard synth modules to it and a granular module. But in any case, I'll be showing you these granular experiments in a second. I just want to show you a place where I found a good reference on granular synthesis. This is programming electronic music with Pure Data. Well, here's the official page for it, by Johannes Kreider. Programming electronic music in PD, actually just PD. And I was looking through this, and I saw here one of the Spanish translations is by Raul Lacabani. I met him in Buenos Aires. It was about 11 years ago when I was there. Spent 3 weeks in the summer there at the El Laboratorio de la Producción y Investigación de Música Electrónica, something like that. I think it was the Investigación de Producción de Música, but it's basically focused on electronic music. Anyway, I got the chance to meet him. It's cool to see his name pop up again. But anyway, this is the main page of the thing. If you just Google or Bing search programming electronic music in PD, you'll find it. And it's by Johannes Kreider. And there is an English translation. That's what I was looking at here. And more specifically, if you find the right link, you can go to wrong page. No, this one, 3.7, granular synthesis. So this is from that book, chapter 3.7, and this is what I'm working with. The thing is, I redesigned some of this a little bit to suit my own preferences and my own way of teaching you, but I should reference at least a source that I used to kind of gain some of this information. And at the heart of it, you could see a lot of this approach in the patches I made. But anyway, let's get to my patches. So here we go. We're going to start off with a looping sampler. And the reason why is because in granular synthesis, while it can be done somewhat live, there's always a certain amount of delay, because the whole idea is you're streaming digital audio through, and then you're granulating it, chopping it up, And usually after you chop it up, you put it through some sort of control window to smooth out artifacts and snaps. So we'll see how that works as this whole thing goes on. But the idea is, here we're just going to make a table of some recorded audio and have it play in a loop, and then we'll be able to granulate it. But in order to understand the whole process, we're going to start by recording to that table as I introduce some key concepts. So anyway, this patch starts off with a load bang. First of all, turning on DSP, and then it takes the sample rate that you're using and sends it out as sample rate. In the example by Kreider, it's basically just using 44,100, and actually that's what I'm using here. But I've added this extra flexibility to use other sample rates. So if you change your sample rate, it will incorporate it into the design. Okay, so let's look at this. I'm going to zoom in. So anyway, sample rate gets calculated and it gets sent to a symbol's $0 sample rate. Now that $0 sample rate appears some places in the patching here where that is used. So whenever you see that, that means this is our sample rate. The $0 is something I use at the beginning to make it a unique symbol for this patch loaded from file. If you've seen some of my other episodes, I do this a lot. Basically, this file loaded from disk, if you put a $0 next to your symbols, and you have something else that you're incorporating that's from a patch file that you load into a parent patch, if it has the name $0 sample rate, it won't be confused with this $0 sample rate loaded from this file. If you don't quite get that yet, don't worry, it's not important to the whole understanding here. But in any case, after that I have this here that is our recording mechanism. Basically, it takes an ADC, this is the sound input, analog to digital converter, the left side, because it's mono input that I'm using, and a mono microphone, and then it gets written to sound file. But you send to write SF commands, and I just made it a simple mechanism here where I can click on the toggle box, and when it's on, select 1, 0, says okay, let's put a bang out 1, the first in the list of options here, and then what that does, that triggers 2 bangs to occur. The right one happens first, which sends this message saying open sample.wave. So we're opening the file that it's getting written to, and then start comes immediately after. So it starts writing to that sound file, but it needs the file name first. So that's why it's right to left is the order of PD in operation. So this goes first, then this, like an instant later. And then when the 0 comes through here, like you uncheck this, the 0 is this outlet here, so that bangs this to happen. The rightmost one, the first one, is to stop writing, and then the second bang comes through where it loads this file from disk to the table. Now the table itself is named $0-sample, and I found in a message, if I were to use the command read-resize sample.wave and then the name of the table $0-sample, I found it ignored the $sign and just thought of the table name as 0-sample, so it didn't find it. But somehow by making a symbol box in $0-sample and banging that through where it replaces this variable here, $1, basically it allows me to use the name $0-sample. So that's all this is just allow me to use that name. So this command is saying, okay, read this file, sample.wave, resize the table to the size of samples in the file, and write it to this table, which here the $1 is a variable that gets replaced by this symbol coming through $0-sample, which is the name of our table. So it writes it to the table, and that's done by SoundFiler. And then SoundFiler outputs the number of samples that the sound file takes up. And I have that sent to this symbol, sample size. So just like before we have sample rate that gets sent, there's also a sample size that gets sent to anything that receives it. Sends go to receives that have the same symbol name. And so sample size is something that eventually goes to more receives and stuff. So here's where it gets calculated and sent immediately, so we know what the size of our sample is. Now when I'm using the term sample here, I mean the recorded file, because in our musical terminology we call a recorded file like that a sample, although really a sample is just a specific calculation of a voltage current that gets recorded. I'll get to that in a minute, alright? But in any case, the word sample will be used in two different ways as I talk about this. But anyway, here, this is where it receives sample rate, and all this is a divider. I just have it set up with this trigger bang float to make sure that whether the sample rate comes through or the sample size comes through, it will always calculate. It will always divide. If you divide the sample rate by the size of the table in samples, you'll get a number here. And this number we're going to use as a frequency value in order to control playback of the table. Okay? Let me record something first, and then I can explain this further. Okay, I'm recording something now. This is supposed to just be an example of some recorded thing that I am making. Oh yeah, indeed. Okay, so here's what I just recorded. And basically, if we were able to zoom in on this, you would see it's made up of a series of dots. And these series of dots makes up this picture. Each of those dots is really a sample. The microphone I'm using goes into a sound card, and the sound card has an analog to digital converter where it interprets the voltage current of the microphone going into it, which gets amplified. And then when it interprets it, it basically, at the sampling rate, samples the voltage current. And that's what we mean in digital audio by sample, as its real definition, is it measures the voltage rate. And the voltage rate of sound, of course, will fluctuate just as sound pressure fluctuates in the atmosphere. So this voltage current that's fluctuating in the shape of the sound wave gets interpreted at the sampling rate, and right now we're using 44,100 samples per second. So if you're interpreting the voltage current's present state 44,100 times per second, you're getting 44,100 different dots for however long this, you're getting 44,100 of them each second for however long this thing lasts. And so if you were to play this back at the sampling rate, it'll play back at a normal speed going through all these dots and playing them back. That's the whole principle. Now here what this calculates is, okay, if we divide the sample size, which since it's more than 1 second is more than 44,100, by the sampling rate, you're essentially getting the time in seconds here in an inverted way. Basically it's saying if we were to play this back at, and I call this the normal rate, meaning if we're going to play this back at a frequency of 0.093, we will be getting the sample rate being played at normal speed, because the mechanism we're using to play back is over here. We're using tab read. What tab read does is, as it's sent at the audio rate, it's a star tilde here, as it's sent the sample numbers in order, it reads that sample and outputs it to the DAC, which is our output. So basically it's like playing each one of these dots. You send it numbers going 0 to 44,100, and it'll give you, if you send it at the right speed, it will give you the samples at each of those points in time, 0 through 44,100, each of those sample locations. It'll give you that value, and when you shoot that out to your output on your sound card, you'll hear it. You'll hear the sound as it is. So what this normal rate is doing, it's interpreting how fast we have to play it back in order for it to sound normal speed. And it sends it right here to this float box where it gets stored. And when you hit the toggle button here, it will bang this float box through. It'll send that frequency 0.39 or whatever, 0.93. It'll send that frequency to phaser. And what phaser does is it's like an oscillator, but it goes between 0 and 1 and then back down to 0 again. So if we multiply its output as it goes from 0 to 1 by the sample size, which is the total size of this table, as you see, it's 471,872 samples long, meaning it's almost about 10 seconds because it's 44,100 samples per second. It's a little more than 10 seconds, in fact. And so that's its total size. If you multiply that by the 0 to 1 operation that's coming out of phaser right here with the star tilde, because we're multiplying by it functioning at the audio rate, it'll truly be going from 0 to 471,872. And so it'll be going from 0 to 471,872, which is over here, the last sample of the table. So this table is really containing 471,872 different points. And so and I guess technically since the first one's 0, the last one is 471,871, because 0 is one of the samples in this total here. So it's one less than this number is the last sample. But in any case, it gets multiplied 0 to 1 by this number, and so it's really going from 0 to 471,872. Okay, so it's playing through each of these samples, and if you play it at this frequency here, which is the sampling rate divided by the sample size, which is that 471,872, if you divide those by, you get that as a 0.093. If you play phaser at that speed, it will go through this table at normal speed and sound like normal. So let's hear it. Okay, I'm recording something now. This is supposed to just be an example of some recorded thing that I am making. Oh yeah. Okay. Now what happens is, since phaser goes 0 up to 1, but we multiply it here, so it goes from 0 up to 471,872. When it's done doing that, it goes back to 0 again, because phaser does that. It goes 0 to 1, 0 to 1, 0 to 1 at the frequency you give it. So here, as a result, it's going, with the multiplication, it's going 0 to 471,872, then back to 0 again. So we really have a loop going here. Oh yeah, indeed. Okay, I'm recording something now. This is supposed to just be an example of some recorded thing that I am making. Oh yeah, indeed. Okay, I'm recording something now.
All right.
This is supposed to just
Now
be
what
an
I'm going to
example
do
of some
is
recorded
alter
thing
this frequency
that I
a
am
little
making.
bit.
Oh yeah.
Now I'm going to just
yeah.
type it in.
Indeed.
But if we were to double
Okay,
this,
I'm recording
this would
something
be
now. This is supposed to just be an
0.18.
example of some recorded thing that I am making. Oh yeah.
0.186. It looks like.
Okay, I'm recording something now. This is supposed to just be an example of some recorded thing
that I am making. Oh yeah, indeed.
So that's
okay, I'm
twice
recording
as
something now. This is
fast.
supposed to just be an example of some recorded thing that I am making. Oh yeah,
But you can also click on
okay,
the
I'm
number
recording something now. This
box
is supposed to just be an example
and
of some
scroll
recorded thing
through
that
it.
I am
But
making.
since these
oh yeah,
numbers are really
okay, I'm recording something now. This is supposed to just be an
0
example
point
of some
numbers, the
recorded thing
number
that I am
box
making.
scrolls
oh
through in
yeah,
integers, so we'd be going way
okay, I'm
too
recording something
fast,
now.
way
This
too
is supposed to just
slow,
be
or
an example
something
of some
like
recorded
that.
thing that I am making.
So I forget what the original is. What
okay, I'm
is
recording
it?
something now. This is supposed to just be an example of
0.93?
some recorded thing that I am making. Oh yeah, indeed.
Okay,
I'm recording something now. This is supposed to
0.93.
just be an example of some recorded
Let's
thing
put
that I am
in
making.
half of that,
Oh yeah.
which
Indeed.
is
Okay, I'm recording something now. This is supposed to just be an example of some recorded thing that I am making.
6.5.
Oh yeah. Indeed. Okay, I'm recording something now. This is supposed to just be an example of some recorded thing that I am
Well,
making. Oh yeah.
not 0.5. Oh, wait a minute. 0.465. So that's half speed there. Because we're playing back at a slower rate than the sampling rate, so it sounds pitched down and slower. Consequently, it's also longer because it'll take longer for phaser to reach the end here. So, as long as you understand this concept, we can move on from here. Because what we're going to do with granular synthesis is we basically chop up this stream into chunks called grains and work with them from there. So I'm going to call up my next file here. Let's zoom out. Alright. And I'll even close the PD window here so I don't get a bunch of them open. Alright, so now here we're actually going to start granulating. This stuff is largely the same. This is the same recording mechanism. Same low bang doing initial things except for one other thing. It's making a default of something called window size. And we're going to get to that in just a moment, what window size is. But it's making that window size, here, zoom in, 441. Ooh. Let's fix that. Yeah. I'm a little... Hey, Crafty likes it this way. He wants it things nice and clean. Alright, so this playback mechanism is the same. It's sending out the sample size and stuff. But by default, we have a 441 window size. And we'll see what that is in a moment. Over here, this is the same calculation where sample rate is divided by sample size, and we get our normal rate. But then we get something else here. We have sample rate, and this window size gets received here. And so we divide the sample rate by the window size, and we get something that I'm calling normal speed. Now, what a window is let me record something in here so we have something. Hello, let's record something into the table. Okay, so we have something recorded into the table here. Now, what a window size is how large in samples will be the chunks that you chop out from this waveform as it plays back. And what you do is you basically play back chunks by chunks by chunks by chunks. So instead of just playing through beginning to end at different speeds or whatever, you are playing through different windows, which are just the chunks that the table gets divided up into. And these sizes of these chunks is called window size. So these chunks are really what are called windows in granular synthesis. And so since I put a default of 441 samples, each second, if we wanted these chunks to be seamless, each second there would need to be 100 of those windows, or 100 of those chunks being played back to back, because our sampling rate is 44,100. And that's what gets calculated here. You see our normal speed is going to, and that means the speed at which the windows are played, or these chunks are sent out. That's 100. So that means like 100 times per second, which totals to 44,100 overall, because each window is 441 samples in size. So 441 times 100 equals 44,100, and that gives us our normal speed if we play it back at a rate of 100 samples per second. Now let's go over here. Here we have our same playback thing, our same playback mechanism that we had in the last example. It just looks stretched out because I had to pull it down to connect up some things here and have it look nice. But it receives the normal rate, so it can play back at normal speed, and if I were to change it here, phaser will be playing back at different speeds, and we'd hear it speed up or slow down, and the pitch would go up or down based on what I put in there, just like the example before. And here's where the sample size gets received, because that gets multiplied by phaser that's going 0 to 1. So this is largely the same as before. I just added a little extra mechanism here to kind of like turn the sound off when it stops, so that we don't hear it playing the last sample played, like, this turns off the sound down here by going through a pack F50 and a line tilde to smooth it out. It basically shuts off sound, and it also turns on the sound when it's time to play back. So that's still part of this whole mechanism I set up for the toggle. Now over here is where normal speed gets received, and it's 100. And what it's going to is another phaser that goes from 0 to 1. And it gets multiplied here, just like it did over here. But this time it's getting multiplied by the window size. So, if it's being multiplied by 441, this is basically making phaser go between 0 and 441. Okay? So this is playing our windows. And if it does that 100 times per second, it'll be going to 0 through 441 to 100 times per second. It'll basically be functioning at the sampling rate. But realistically, what's coming through here is 0 to 441, 0 to 441, 0 to 441. But we use this sample hold, or it's actually called samp hold tilde, object to connect these two systems. Basically what happens is through the left inlet is where you put your signal. This is our signal, because this is playing through the whole table. 0 up to what its current size is. This one is 153,024. Okay, so that's how many samples long it is. And so that's what phaser's going through, 0 to that number. And it's going through it at the normal rate, which doesn't get displayed yet. It's stored here. It will come into this number box when I press play, which I can do now. Hello, let's record something into the table. There we go. I just stopped. And it goes away again because the 0 goes through to shut down phaser. But anyway, for a minute there, well, we could see the number down here. Here's the frequency, 0.28. As you see, this is a larger number than the 0.39 we had before. But before we had a larger table. So, since it's a larger table, larger file, you play it at a slower frequency to get through the whole thing at normal speed. This one is a higher frequency because it's a shorter table size, shorter sample size. So one sample at a time, you go through faster rate because there's a shorter length. The whole idea is to keep those samples coming at 44,100 samples per second to match our sampling rate, and then things will sound normal. So it's like tapes being played back at the right speed. So anyway, these are coming out 0 to 44,100, and then from 44,100 up to 88,200 in the second, and so forth. When they're played at the normal rate going into samp hold, that's the type of numbers coming in here. Now what this does is the right inlet is called the control inlet, and what it does is it basically outputs the value that's coming through here. Now remember, the numbers that's coming out of here is really a sample strength number. It's where it is the position in the waveform between 0, 1, and -1 down below. So it's getting a number like that. It's just indexed in time 0 to 44,100. But let's say at 1 second, the index value 44,100, where we're at that point in the table here, this thing is shooting out the number 44,100. Okay? So I was incorrect before. It's not shooting out where we are in the table. Tab read does that. Basically, it's shooting out the number 44,100. And out of here, phaser is going 0 to 1. By the time it gets to 1, it then drops back down to 0 again. And the way samp hold works is when it drops down to 0, that's when it spits out the number here. So this thing drops down to 0 100 times per second, each 441 samples. So it goes 0 to 441. It gets counted as 441 here, but really it's the same point in time. This thing reaches 1. And so when it drops to 0, samp hold then shoots out the number that's here. And at that point in time, it should be 442. So that gets dropped out here where it's added to what's coming through here. This is going 0 to 441. The time it gets to 441 and then goes to 442, this goes back to 0, and this shoots out a 442. So what we're getting, and it'll happen by the time we get to 882, which is the second window size. When that happens, this returns to 0, and it gets added to the number 882, or 883, I think, at that point. And so it goes into tab read, and tab reads the table here to see what the voltage is at that point, or in this case, it's the digital number in the table. And so that number gets sent out here, and as long as these are sent at the audio rate, we're going to hear an audio stream coming out of DAC. But that's what sample hold is doing. It's allowing this to control the number stream here, so that if things are played at the right speed, everything's fine. Let's record something into the table. But now we're going to hear some granulation. Hello, let's record something into the table. Because I'm going to change the number here. Hello, let's record something into the 200. Table.
Hello, let's record something into the table.
So now the grains that we're chopping up here, or the windows that we're cutting into slices, are being sent faster. So it sounds like an uptune in pitch, but you also hear this graininess because it's being sliced up. Now let me do it slower. Let's go down to 50 here. Half speed. Okay, so now we are hearing the grains coming out at half speed. So the grains are controlling how quickly the sound is being sent out. But since it's chopping it up, we hear all these little snapping sounds in between. And that's what we're going to fix next. The way you fix that is by using another table as a control to put a shape over the amplitude. So this patch, let me zoom out, is the same as the one before, except we're now adding, and I'll point this out later, another tab read that is putting this table on top of each grain slice. So as it chops this up and it shoots out these chopped out things from tab read, it puts this over them like an envelope, which helps keep them from snapping because it's shaped. It's called a Hanning window, and this is its shape. It's really a cosine curve going from 0 to 1. So its shape goes from 0 sloping up to 1 and back down to 0 in the cosine function, giving it this shape. And then here, this tab read, at the same speed it's reading these windows, it's reading this, and this gets multiplied down here on the amplifier. So basically each one of those grains gets enveloped by this before it gets shot out, so it sounds smoother. This is the only additional thing, except I had to add this here to generate it. This is basically a mechanism to generate this table, and we can look at that real quick. To generate this Hanning curve, we need to basically, here's the symbol thing again, going to the table. It's resizing the table and stuff based on this that comes in, the window size. So the window size starts at 441, but I made a mechanism here so you can change it. So when the window size gets changed or whatever, it recalculates this table size. This table size needs to be the window size. So this is currently 441 in size. And this shape basically goes over it. It's the envelope. And so anyway, normal speed comes in here, because normal speed, which we got before from this function here, and I send it through here to make sure it gets here in time. But basically, this oscillator that generates this shape, its phase is 0.5, and then I have it added +1, which basically puts it in the range of 0 to 2, and then cut it in half, 0 to 1. This makes a normal oscillator, which does the sine function, basically do it from 0 to 1 instead, and then its phase is 0.5, so we get this nice cosine shape. We get the shape that we want. So this oscillator just gets written to the table to give us this shape. And when you change the window size, it automatically will give you the right size table, and the shape will go over it. Okay? And then that shape is what gets multiplied here. Here's the tab read that reads the shape, and it reads it at the generation of the window rate. So 441, each 441 samples, every 441 samples, it reads this table and multiplies our sound signal coming out of tab read by it, which means it's like an amplitude envelope that is shaping each one of those grins or windows that are coming out. Okay, so let's record something to see how this sounds. And so I have this once again with defaults so that it plays back at the normal rate. Okay, so let's record something to see how this sounds. But it sounds chopped up because I have this thing chopping it up. How this sounds. 100 times per second. Something to see how this sounds. So it sounds like amplitude modulation, really, because that's what it is. It's basically, if we slow this down a lot, it would sound like whoop, 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 whoop type of stuff. You would actually hear the amplitude fluctuating. But since it's happening so fast, 100 times per second, it just sounds kind of grainy. But it doesn't have the higher pitch snaps that we had before. In the next step, we get to take this out. We get to take out the graininess even more. But let me show you something first. Let me make a window size of 22,050 is half the sampling rate. What's a third of this? No, let's chop that in half. A fourth of the sampling rate. 11,025. So basically, we're going to get how many windows per second? 4, because we chopped the sampling rate up into 4 slices. But this is now resized. This table is now 11,025 samples wide, and this shape is still going to be our amplitude envelope. But now we're going to hear like 4 fluctuations per second. Okay, so let's record something to see how this sounds. Okay, so let's record something. So before, that's what was happening, except it's happening 100 times per second. See how this sounds. Okay, so let's do this to where we hear just 2 of them. Then it'll be really obvious. So let me do, this is half the sampling rate, 22,050. Okay. Let's record something to see how this sounds. Okay, so let's record something to see how this sounds. Okay, so let's record something to see how this sounds. Okay, so let's record something to see how this sounds. Now, that was just so you can hear it, but when we're trying to do things in a granular way, you definitely want smaller window sizes. Let's try something like, we had 441, 2 times that is 882, 2 times that is 1764. So now we'll hear graininess again. So let's record something to see how this sounds. Now let's change the speed of these grains.
Let's record something to see how this sounds. Okay, so let's record something to see how this sounds. Okay, so let's record something to see how this sounds.
Okay, now let's change the speed here. 0.29, let's try
how this sounds.
0.5 or something. Almost twice as fast.
See how this sounds. Okay, so let's record something to see how this sounds. Okay, so let's record something to see how this
Let's try
sounds.
roughly half
Okay, so let's
speed,
record something to see how this sounds.
0.125 or
Okay,
something
so let's
like
record
that.
something to see how this sounds.
So our grain speed is slow, and so is our playback speed. But let's speed up the playback speed and keep the grain speed slow. Sounds pretty cool. Let's try 0.5.
Okay, so let's record something to see how this sounds. Okay, so let's record something to see how this sounds.
Now,
Okay, so let's record something to see how this sounds.
I said that we're going to make this even smoother, and this will be our last example. Oh no, second to last. But basically the last major change. What we're going to do is we're going to have two instances. You see how this is a pair? Where we have a tab read reading this table, our sound signal, and one reading this table, our envelope that goes over the grains. We're going to double this, and then at the same time that we double it, we're going to take the double and put it out of phase. Essentially what we're going to do is have like a crossfade between these. If we have two signals where this one's going in and then going out, and the other one's like inverted in phase, basically you'll have a second signal going in while the other one's going out. So you'll just have this little section here where you have a dip, but it doesn't go all the way down to 0, but you'll have a dip because the other one's fading in. And so you have some graininess that sounds smoother, is what happens as a result. It could be done two ways. You could really just have a second table, second tab read, and just put it out of phase. But the patching in Kreider's book is more like this, although his patches are simpler. It's the same idea though. Here we go. Let's open this up. I'm basically going to use the same table. Don't need a second table because it's the same shape really, except as Kreider puts in his book, we have here the phaser output getting multiplied by 0.5. Since this phaser is going 0 to 1, what happens here is now 0 to 0.5 becomes its range. But by doing this, where we have this thing called wrap, well, no, 0.5. Basically, it goes up to, yeah, it's out, plus 0.5. Sorry, see, I'm zoomed out. There we go, plus 0.5. So we're going from 0.5, because 0 plus 0.5 equals 0.5, up to 1 plus 0.5 equals 1.5. So now we're going between 0.5 to 1.5. And then when we put it through wrap, what wrap does is you can have it, anything that goes above 1 gets wrapped back around between 0 and 1. So in other words, it forces it to be going from 0.5 up to 1 and then down back to 0 up to 0.5 again, which is essentially changing the phase. So what it's doing is, as this tab read goes through, it's reading through this table, starting here, going here, and then back to here, like this. At the same time, the other one's starting here and going to here. So it's basically 180 degrees out of phase is what's happening. And it basically still needs to do the same thing where it takes in the tab read of the other signal too. And this one also is going to be, as it's coming through, the sound signal then gets this amplitude envelope over it. And it gets this amplitude envelope over it. and then the two get added together. So we have the two signals coming through added together. And since they're out of phase with one another, basically the sound, just imagine a sound wave inside this curve here of one of them, and then the same sound inside the other one that's a shape like this. Basically, as one sound fades out, the other one's fading in, and you hear a smoother graininess basically. So let's record some sound into this table and see what we get as a result by using this out of phase or phasing, two-phased phaser things, reading tables. Yeah. Okay. Let's turn it on. So let's record some sound into this table and see what we get as a result by using this.
Here's
out
our
of
100
phase
because we're still at the
or
default
phasing,
441 window size.
Phaser things.
Here's where we can change the playback speed. Let's say.
So let's record some sound into this
Let's
table
try
and see what we get
that,
as a result by using this
0.134
phase or phasing, two-phased phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase.
So now it's going through
phasing, two-phased
twice as fast.
phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase or phasing.
Now let's change this.
Phaser things, reading tables. Yeah. So let's record some sound into this table.
Change
and see
the
what we get as a
grain
result by
speed.
using this out of phase or phasing, two-phased phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase or phasing, two-phased phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase or phasing, two-phased phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase.
Now
or
let's slow this
phasing,
down.
Two-phased phaser things, reading tables. Yeah.
What
so
was
let's record
it?
some sound into this table and see what we get as a result by using this out of phase.
0.67, I think.
Phasing, two-phased
So
phaser
let's
things,
make
reading
that
tables.
in
Yeah.
half approximately.
So let's record some sound into this table and see what we get as a result by using this out of phase or phasing, two-phased phaser things, reading tables. Yeah. So let's record some sound into this table and see what we get as a result by
Oh,
using
no.
this out of phase or phasing, two-phased phaser things. Yeah. So let's record some sound into this table and see what we get as a result by using this out of phase or phasing,
Two-phased.
there we go.
Phaser things, reading tables.
Yeah.
Let's record some sound into this table and see what we get as a result by using this out of phaser.
Alright, so you could spend hours doing fun things with this. Alright, let's zoom out. And then there's one last one. Now here, there's no real addition to the patching. I just added some better ways to control those speeds and stuff up there. I basically added some sliders here. In each of these slider pairs that I have, the right slider goes above and the left slider goes below. And basically I multiply the normal speed value by these numbers. So these numbers coming out of sliders are really a range of, in slowing it down, 0.01 up to 1. In speeding it up, a range of 1 up to 100. And I have those pairs for both. So that way, basically, by using the multiplier here, I'm changing these numbers, and it was just an easier way of doing it rather than, like especially this side here, where typing into this number box floating point numbers is kind of annoying. I'd rather slide on a slider, so let's do that. First, let's record something. Okay, now I'm going to record something again for the last time because we're just about done with this episode, and I hope you've enjoyed it. Okay. Playback, let's turn it on. I hope you've enjoyed it. Okay, now I'm going to record something again for the last time because
So
we're
here's
just
the
about done with this
playback
episode,
rate.
and I hope you've enjoyed it.
Let's slow it down.
Okay, now I'm going to record something again for the last time because we're just about done
Now here's
with
the
this
grain
episode,
speed.
and I hope you've enjoyed it. Okay. Slow this down further.
Something again for the last
was normal speed. Yeah, so I sped it up a bunch, and now slowing down the grains. Whoa, sorry.
Okay, now for the last time.
This episode, and I hope you've enjoyed it. Okay, now I'm going to Alright. Yeah, I hope you enjoyed it. Okay, folks, so that's granular synthesis, understanding the darn thing. Okay, so, as usual, if you have some questions, drop them in the comment box. Other recommendations, you can drop them there too. Keep it positive, keep it constructive.